In this video, I'm going to connect Fourier series to vectors and to linear algebra in general, and also at the end make a connection to quantum mechanics. This is certainly extra credit material. None of this will be tested on an exam or anything, but I would still recommend that you watch this video because it might give you some insights and help you understand some of the concepts that we will cover later in this course and in other courses. So we already know about vectors. They're fundamental to what we're doing in this course. The way we treat them so far is that we think of them as arrows that have a magnitude and a direction. And we can do different things with them. Essentially, we have two different mathematical operations we can carry out on a vector. We can add them together, or we can multiply them by a scalar. This means that we can take a vector like this one here and we can decompose it onto unit vectors. So if we take a unit vector here and one there, and this is going to be E1 hat and E2 hat, then I can take this vector and I can decompose it onto two other vectors like this, where this vector will be U1, E1 hat, and this vector here is U2, E2 hat, right? Or if you write that down here, we have that the vector U is U1, E1 hat plus U2, E2 hat. And that's essentially applying the two operations we can on a vector, addition and multiplication by a scalar. This is of course known as vector decomposition. And the other thing we need to do the manipulations that we want to do are scalar products. So the scalar product of U with V is of course the magnitude of two vectors times cosine of the angle between them. Okay, so that much we know quite well. We can rewrite this if we like, this vector decomposition as a sum. We are doing it here in 2 dimensions, but nothing stops us from increasing the number of dimensions to 3, 4, or however many that we need. So in general, we have this sum here, and n, that's the dimensionality of the vector space. Right, so if we're working in 3 dimensions, then n is 3. If we're working in 12 dimensions, which is mathematically possible, then n would be 12. Okay. Also, if this basis is orthonormal, then that's the same thing as saying that the scalar product of vector E hat sub I with vector E hat sub j is delta ij. Okay, and that means we can actually easily find what these u's are here. We can just take the vector u and scalar product with the ith basis vector, and we will then get so that makes it easy to find the components here of each individual vector. Okay, so these are things you already know. So why am I telling you this? Well, it turns out that in mathematics, the notion of a vector as an arrow, as something with magnitude and direction, is not fundamental. Mathematicians like to generalize things, and what really makes a vector is the mathematical operations you can perform on it. That is, you can add them together, you can multiply by a scalar, and then you can also, if you like, at least in most cases, define a scalar product. Right. So to have a vector, we don't need to look at it as an arrow. What we need is for the vector to fulfill what are known as the vector axioms. And these are these, right? And basically it says if you take a vector, you multiply it by a constant, and add it to another vector that's been multiplied by a constant, then what you have is still a vector. Right? You have a vector space V here. And there's also such a thing as a zero vector, that if you add it to another vector, you get back the original vector, and you have an additive inverse. So there are two vectors that are opposite one another. If you add them together, you get the zero vector. And the rest are essentially just properties of multiplication and addition. They're included here because if you want to generalize the concept of a vector, you don't have to define addition and multiplication the way you normally do. The scalars a and b don't have to be a number, and these vectors here don't have to have a geometric interpretation as an arrow in some Euclidean space. So that's what we're going to do here to some extent, although we will keep the definition of addition and multiplication to be what they normally mean, and we're going to have our scalars be real and or complex numbers, but we will change what we mean by a vector. The other thing that we need, of course, as well is a definition of the scalar product, and that's not then in general tied to this geometric definition. Instead, what you need in order to have a scalar product are the following. A scalar product is a binary operation on two vectors that yields a scalar, and it has certain properties. It has what's known as conjugate symmetry, that if you take the scalar product of u with v, you get the complex conjugate of the scalar product of v with u. Okay. I should also mention that if I write u dot v, I'm using a slightly different notation here. The reason is twofold. First of all, I want to emphasize that this is actually a mathematical machine that takes two vectors and turns them into a number. Second, this is actually the notation that's normally used in quantum mechanics. So you need to be conjugate symmetry. We need to have linearity in the first argument, and it has to be positive definite, so that you take a scalar product of a vector with itself, you get a real number larger than 0, and if that number is 0, that means that the vector is the zero vector. So this is what you need in order to say that you have a vector. So this means that any collection of mathematical objects that satisfy these axioms can be treated as vectors in a vector space. So let's give an example. In fact, a very important example. So we're going to keep addition and multiplication to be their normal definitions, and we're going to keep scalars here to be real or complex numbers. But we're going to say that our vectors are periodic functions. Right? And for a given period tau, all such functions, if they are well behaved enough, form a vector space. And by well behaved, I really mean that we can use them to define a scalar product in a certain way that I'll mention in a second here. But if that's the case, if these are our vectors, and it's kind of hard to see them as arrows, but if they are vectors, they should satisfy the vector axioms, right? So let's say that we have some h of t, which is a scalar of f of t plus a scalar b times some other periodic function g of t. And that means that if f is periodic with period tau, and if g is, well, that means that so is h. So we have this first condition satisfied. That's the closure. The zero vector is just functions equal to 0. Then this is true, right? And all the other things here are just properties of addition and multiplication, and we haven't changed those definitions, so we know that this is actually periodic functions are actually good vectors, surprisingly enough. The only thing other that we need to now identify or define is a scalar product. So let's do that. We're going to have a scalar product of two periodic functions, which we write either with a normal dot product or with this bracket notation here. And we're going to define this as 1 over tau times the integral from 0 to tau of f of t times the complex conjugate of g, in case it's complex, to t. That's a scalar product. So if all this works now, we should be able to take our vectors, which are periodic functions, and decompose them onto a basis, just like what we did with our regular arrow as a vector original geometric definition. Okay, so let's see how that works out. So we have f of t. We should be able now to put this as a sum, where n goes from 1 to some number n of, let's say, c of n times our unit vectors. Now these unit vectors are just like these vectors, periodic functions that depend on time. What we would like, though, in order to be able to calculate these vectors here, or these components here, c of n, using this method, is that we want an orthonormal basis, right? We have done this. In order to calculate the components, we want an orthonormal basis where this is true, so that we can find the components with this formula. So let's see how that works out. That's what we need, right? And if that's the case, we know that the c of n is just going to be equal to the scalar product of f with the corresponding unit vector. Okay, so I'm just repeating these two equivalent notations here, just so that you get used to both of them. So to see how this might work, let's make a choice of basis vectors. There are more than one, obviously. There's always more than one choice of basis vector that you can use. That's the choice of our basis vector. They're going to be exponentials. And of course, it's just a pure accident you have an e here and one here. They don't mean the same thing, of course. This is just to indicate a unit vector. This is the basis of the natural logarithm. Okay, so if that's the case, we should, if everything's working out, have this be true. So let's test that. And this minus sign here is because we need a complex conjugate in there. Now you've seen this before. This is when you did Fourier series, so I'm going to do this very rapidly now. Okay, so it works like we expected it to. So, in other words, we can just write just like we already knew we could from Fourier series. But what we've done here is that we've reduced the decomposition into a Fourier series into a decomposition into basis vectors, which is exactly the same, done exactly the same way as for regular vectors in 3 dimensions. The main difference is that we are working here in an infinite dimensional space. That has some consequences for issues of completeness and convergence and all that, but as physicists, we're not going to worry a whole heck of a lot about that. So we can just simply say that Fourier decomposition is the same thing as a vector decomposition in an infinite dimensional space. Okay. So this is exponential Fourier series. We can do the same thing with the sine and cosine series. That's just different choices of basis vector. Which should look familiar, except for the factor of square root of 2 in front here. That's just there in order for this equality here to be true. Without it, you would get 1/2 there, but that's a minor issue. So that means that we can also write which is then of course equal to so Fourier series decomposition is just like vector decomposition if you interpret the function that you're finding the Fourier series for as a vector, and that works just fine. The analogy can be quite useful in other contexts. So for instance, if I want to calculate, let's say, the RMS value, root mean square amplitude of some function f of t. So that's the square root of the average value of f squared. Right? So I need to calculate the average value of f squared. Okay, f is a periodic function, so I can do that in the following way. Okay, but interestingly, that's just the scalar product of f with itself. Right? And since that we know that we can write down f on this form right here, that's what we're going to use, then this becomes relatively simple. And again, this is just a scalar product of these two vectors here. Okay. So what this says is just that the average of the function squared is just the sum over the square of all the Fourier components of the of this function. This you might recognize as one version of what's known as Parseval's theorem. But it's really the same thing as Pythagoras' theorem in infinite dimensions, interestingly enough. Also, just for completeness, we can do the same thing with the cosine and sine values here. So we will get then that that's the same result, just with a's and b's, and this factor of 1/2 again comes from this square root of 2 that we need to carry around because of normalization. We want to be working with an orthonormal basis. Okay, so that's kind of interesting. So linear algebra comes back in context where you might least expect it, and in fact we can take this analogy even further than this. We know that when we're working with vectors, one of the things that you did in linear algebra was that you had linear operators that acted on your vectors, right? So you could take a linear operator A and act on vector u, and then you get another vector v back. So in finite dimensions, this was represented generally by matrices. So just to give an example of how this might work, you're familiar with the eigenvalue, the concept of eigenvectors. So if we take, say, an operator A that acts on a vector u, and then you get back the same vector but multiplied by a constant. This is known as the eigenvalue equation. Okay, so this is the operator. These are the eigenvectors, and here we have the eigenvalue. You should have done this already a number of times, and you know, of course, that if we're working in, let's say, 3 dimensions, we can have, just as an example, have the matrix 2, 0, 1, 0, 2, 0, and 1, 0, 2, acting on the vector 1, 0, 1. Turns out that that equals the number 3 times your starting vector 1, 0, 1. Right? So by the color code here, we see that this vector here is the operator, and this is u, and here we have lambda. Okay, so that's in 3 dimensions. Let's do this now in an infinite dimensional space, using our concept of functions as vectors. Okay, so what you might get then is the following thing for an eigenvalue equation. So this derivative here now is our operator A, the function e to the alpha x, that's the vector u, and a constant alpha, well, that's our eigenvalue, lambda. And this works as long as the operator you're working with is linear, and derivation is linear. So this is an exact analogy of that, but in infinite dimensions. It turns out that in quantum mechanics, particles are described by wave functions, and those wave functions are actually being treated as vectors in exactly this way. And that's really why I did this, not only to give you a convenient way to understand Fourier transforms, but also to give you a little bit of a preview on quantum mechanics, where you will use this analogy all the time.